Hey everyone, welcome back to another video by Camroom 5. In these sets of videos, we're going to be talking about the organic chemistry for A2 level. Particularly, we're going to talk about benzenes, also known as arenes. A lot of medicines that we deal with in our today's life have this 6 carbon compound, which has a very weird thing about the pi bonds it has that is known as the pi bond resonance. So basically, benzene, which we're going to be talking about in today's video, is a 6 carbon compound which is quite unsaturated that it has 3 carbon carbon double bonds. But those carbon carbon double bonds normally don't show those common properties of a pi bond. That's why we're going to talk about the structure of benzene before we can talk about the properties. Benzenes are also known as arenes. So when we talk about them, there are 6 carbons in a single plane. Each carbon is bonded to a hydrogen as well, and they have a pi bond between each other, but the pi bond keeps resonating, keeps changing its position. And in order to understand that, we need to know that each carbon over here in benzene is sp2 hybridized. Each carbon atom is sp2 hybridized, which means that one s orbital and two p orbitals were combined together to make 3 sp2 orbitals for each carbon. You can see the blue orbitals are the sp2 hybrid orbitals, while the yellow ones are the unhybrid p orbitals. Each carbon has an unhybrid p orbital which is totally perpendicular to the other sp2 orbitals. You can see each carbon has those sp2 and unhybrid orbitals. The green circles are hydrogens, while the yellow bonds are the pi bonds. These pi bonds keep resonating above and below the plane of those 6 carbons. Now that is really important, that those 6 carbons 1, 2, 3, 4, 5, 6 are in a single plane because of their hybrid orbitals, and even the s orbitals of the hydrogen atoms you can see with the green circle are also on the same plane. But it is the delocalized pi electron system, which is the pi bonds, those are above and below the plane of the benzene ring. The benzene ring is hexagon with a proper 120-degree angle between each carbon atom. That is why when you draw benzene, you draw a circle rather than the pi bond. The circle actually shows the delocalized electron rich pi bonds. So this circle represents the delocalized pi electron system, which is not fixed in its position. Don't forget to notice that each carbon is bonded to a hydrogen, but we never show that. Let's consider few molecules like cyclohexene, cyclohex-1,3-diene, and benzene. When you notice a carbon-carbon single bond, which is a carbon-carbon sigma bond, the bond length is roughly 0.154 nanometer. When you pick a carbon-carbon double bond, which is obviously a combination of sigma and pi, the carbon-carbon double bond length is equal to 0.134 nanometer. But in benzene, it's neither a single nor a double bond, it's actually a resonance. That is exactly why the bond length is an average of the single and double bonds. So 0.140 is the bond length, which is between the single and the double bond, which shows that the pi bonds between the carbon atoms are never located, they are delocalized. And these delocalized pi bonds are above and below the plane of the hexagonal benzene ring. We always call it the electron-rich pi bond resonance. You can also call it the pi electron system or the pi bond system. Since there's electron-rich pi bond system, it attracts electrophiles towards it. Now, what's an electrophile? Electro means electron, phile means loving, right? So, electrophile is an electron deficient chemical species. It's an atom or an ion or a molecule which has less electrons, it has a positive charge on it, that accepts electrons, which is in need of electrons, so it will accept electrons, especially from the pi bond resonance system. And that leads us towards the most common reaction of benzenes, known as the electrophilic substitution, where the benzene pi bond system is donated to an electrophile. Now, when we talk about the electrophilic substitution reaction, what's actually happening over here? See, you can see a benzene molecule with the 6 carbon atoms it has. 1, 2, 3, 4, 5, 6. Each carbon already has a hydrogen, but we are not showing them. When there is an electrophile around benzene, one carbon atom picks an electron pair from the resonance system and gives it to the electrophile. The pi bond between carbon 1 and carbon 2 is broken. Why? Because carbon 2 picked the electron pair and gave it to electrophile. As a result, what happens? The entire pi bond resonance is disrupted, and we draw this plus sign and a half circle to show that the resonance is now disrupted because an electron pair from the resonance has been donated outside. Now this carbon 2 made a bond with the electrophile, but to make that, the whole resonance was disrupted. In order to make another bond with the electrophile, carbon number 2 had to become sp3 hybridized. And this happens temporarily. All the carbons of the benzene ring are sp2 hybridized, but this one particular carbon becomes sp3 hybrid for a temporary period as long as the resonance is disrupted. Now, how do we resume the resonance? Since it was disrupted because of loss of electrons, now we need electrons. How do we get electrons? We get the electrons by eliminating hydrogen atom. We take the electron pair from the bond between carbon-hydrogen, we eliminate the hydrogen atom, and we resume the pi bond resonance, and the hydrogen is eliminated as hydrogen ion because both the electrons were now gained by the resonance system. So what's happening overall? In step 1, the electron pair from the pi bond resonance is donated to the electrophile. And when the pi bond system electron was donated to the electrophile, it was to make a sigma bond between carbon and electrophile. What next? As the pi bond system is disrupted, as the resonance is disrupted, how do we resume it? A hydrogen atom from the same carbon atom is eliminated. We eliminate a hydrogen atom from the same carbon atom, and the electrons and the electron pair basically from that carbon hydrogen bond are involved in the pi resonance system, in the pi bond resonance. So these are the two steps of general electrophilic substitution reaction. Overall, the most common reaction of arenes include nitration, which involves concentrated nitric acid and concentrated sulfuric acid to make nitrobenzene. The second reaction involves SO3 gas with concentrated sulfuric acid to make benzene sulfonic acid, where SO3H is attached to the benzene. Another common reaction is using alkyl chloride with FeCl3 or AlCl3 anhydrous, where the alkyl chain is attached with the benzene and we call it the alkyl benzene, like methyl benzene, ethyl benzene, etc. Another common reaction is using acyl chloride with the same FeCl3 and AlCl3 anhydrous, where the acyl group is attached to the benzene. It is known as the acyl benzene. The last two reactions on the left hand side, you can see the purple one and the orange one, they both use FeCl3 or AlCl3 anhydrous. We call these two reactions as the Friedel-Crafts alkylation or acylation. I hope the overall picture is clear to you guys. In the next video, we'll talk about some more benzene stuff. Stay tuned.